So I'm going to begin with the code word is sRNN for simple RNN. I'm going to also refer you to another paper. I think it is in the list, but I'll double check. It's called Basic RNN, and it's theoretically inclined. We're not really interested in the deep theory per se. It's good to know what the general structure is. It follows backpropagation using maybe more technical formulation from constraint optimization, particularly non-convex constraint optimization. And then I'm going to talk again, repeat the so-called the LSTM model. We're going to zoom into the parameter reduced LSTMs, various forms. We talked about 3 last time. We'll just dwell on maybe 2 more of those, and we see where the reduction direction is taking us. These are very simple modifications, but it have very impactful consequences in terms of saving time and improving performance. And if there's an extra time, we can go back to the simple RNN, particularly this code, because this code will be something in the mini project. So I'll give you an opportunity if you have any questions about it. If not, that's the plan. So simple RNN model, we should memorize it by heart right now. And this is the form of it. And H denotes activation, which is the output of the non-linearity. We put a sigma for the non-linearity. And traditionally, this nonlinearity has been hyperbolic tangent, also sigmoidal or logistic function. And more recently, people are using the rectified linear. I'm throwing all these terminologies, expecting that you know what I'm talking about. So these are all key terminologies about the time linearity. We have them listed. We have them in prior handouts, and these are words that people know by heart now, okay? And you can also look at any form of nonlinearity, but these are the dominant nonlinearity forms. And it's a function of, in this notation, I'm using the same notation in some references. XT here stands for input, HT the activation, so you have the prior activation also fed back, and you have a bias. And in some references, you may have the W and U interchanged. I'm keeping the W with the input just to build up on the feed-forward neural network, because I had a W for the feed-forward network with the input. So the U is really for the rectified, for the activation. That's the form. I can rewrite the form by saying what's inside the parentheses here. I'm labeling it as an intermediate variable CT, which is really the state. And then CT is the net input that drives this nonlinearity. So I split into 2 pieces to make sure I have an equation which looks linear. And then this nonlinearity just has an input and an output nonlinearity. And I have this intermediate state, and I'm using the same terminology as this C, the so-called memory cell, okay? Just to connect it to LSTM models. Now, I'm sharing with you here the so-called basic RNN, which is based on some work that we've had, 2 years ago. And I'll give you the reference. It's very simple, the modification. The modification says if this CT, this CT is now interpreted as this state. And the concept of state in engineering and in science and in physics is very important. It's the variable that captures the essence of the information about the model, okay? So you delegate it to one parameter. In this case, we're using this CT. So this CT, the modification of this basic RNN is just inserts a term here that has CT. That's one. Secondly, it just, instead of having this input at T and this one is T minus 1 and this is at T, minor modification just says On this side, we're going to have all the variables at the instant t, and they predict the next variable at t plus 1. This just brings out the prediction. This is a traditional thing in systems and differential equations and science. Okay, just you have this one and one time the other one. And this is nonlinearity by itself. So a slight modification. This A is important in terms of you want this A to be, for instance, one example, to have it a constant, which is in this case we selected to be 0.99 times the identity. This I is just from traditional thing, the identity, right? And so this is a linear term, and this linear term helps stability of a dynamic system, okay? So you could say that's A here could be scalar times the identity, and that scalar has to be between, let's say, 0 and less than 1 in absolute value. And also, to make sure, so this is a recurrent neural network, but if you connect it to engineering, often in engineering we think of transfer function for linear systems. And also, some of you already maybe experienced things. When you talk about transfer function, you can look at the frequency domain, you look at zeros and poles. So you need a transfer function that has a shape that's bandpass filtering in some sorts. You don't want it to be low pass. If you have only the recurrent network, you're going to end up with an effective low passing. If you have the feed forward only, you end up with things that could be high pass. Okay, so there's some concepts about FIR filters, finite, some of you in signal processing about FIR filters, IR filters, and things of that sort. So there are a lot of thinking in bringing the simple things here, that this makes sure that the poles of the systems are, if you wish, stable in a way. And you control this constant. I'm putting here explicitly 0.99, but it could be any number between 0 and 1. And you can reduce this scalar here to make it as close to 0. It has to be less than 1. And the advantage there just guarantees stability of the dynamic system, okay? So there are a lot of things in this one. If somebody's interested in the details, I have a full information in this paper, which appears in the archive.org. And this paper has a basic recurrent neural network, and it's some work in 2016, and it talks about all the nuances beyond our scope here in a way, but what we wanted is just this simple model, this modification, and what brings in. And it talks about why we're doing these little changes, a lot of educational aspects that you can gain from this one that are very simple in picking up. They're not sophisticated, and it talks about the fact that we can look at this effective network as being a transfer function, and this is the model. So this model kind of generalizes in a slight way. It adds this linear term, okay? So, and it also puts things here in one time, and this is another time. It also helps in taking this model and apply it to a prediction scenario. Like if you have a data, right now the models that we have recurrent neural network, the state is at time t, and you use things prior, okay? So this one is a slight little twist by saying, I'm gonna get data at this time, I wanna predict something in the future, one step. So what we want from this one, I mean, I advise you clearly to read, but you don't have to go through the mathematical derivation and what have you, because it gives you a similar model. We don't need to go through these things. This is just you be aware that there's some techniques and technical things that one can pursue. What all we wanted for our purposes is the following, which we have it here. Just this is a minor change to this model. You can even put it in this model here. So if I look at this model, what I need here is something that depends on CT minus 1 with some scalar multiplication, alpha, where alpha is between 0 and 1 in absolute value. Okay, so that's the same. That's the only wrinkle. It's having this linearity. This one also, in a way, relates indirectly to the concept we've seen before in residual networks. When you notice that there is some forward path, just bypassing and having forward path that bypass the model. Okay, so that's really what we want from this one. Nothing, just this. So recurrent network by itself always needs a feed-forward layer to follow it in order for the combination to represent a filtering capability that can perform flexible filtering. When I say flexible, that means it can perform low-pass filtering, high-pass filtering, but also the most thing you're interested in is band-pass filtering, which means it's going to ignore anything above certain frequency, could ignore anything below some frequency, and it looks on a right band of interest. And this is very important. This engineering concept is very important in saying, what are we building here? Eventually, your network or your system, eventually, after training, is going to perform some transformation, which is a form of a filtering. It's going to get rid of all that bad stuff, right? And it's going to capture the essence of the signal that's coming to it. It's going to map that into some classes or some representation. That's the key idea. Okay? So that's the extent of it. So I'm going to have this paper. If it's not there, I'm going to have it there. You just read the introduction. Just know what the discussion is, what the flavor of things are, and you may want to look at the technical derivation if you're interested in. But we're not going to go after the mathematics of that paper. So that's one little level that is close to simple RNN as possible, makes a little modification with this element to avoid instabilities caused by vanishing of gradient or exploding of gradient. So that one little term here could actually help you be able to handle long dependency sequences without going unstable. Turns out that could be a good solution. Now we go back to the base of what LSTMs are, and I'm repeating, LSTMs has been the workhorse of all the applications of recurrent neural networks to speech recognition, speech prediction, language translation. These are or language modeling. These are the key applications that propelled the need for recurrent neural networks in the form of LSTMs. And I'm repeating again here, I'm viewing this one. Here you have the set of gates, and you have the cell memory. And the cell memory, like the set of gates, the only thing, nonlinearity that you keep here is hyperbolic tangent. And the sigma n is really stands for sigmoidal nonlinearity, limiting the gates to be between 0 and 1. And then you have this element, which is exactly the simple RNN form, but you don't map it to the hidden gate. You map it through this sequence of cell memory, intermediate variable, and then the cell memory with 3 gates here gives you the activation, and you could go through the process. And There are a lot of fancy diagrams that try to interpret this one here. They're all in a way equivalent. Some of them are tailored for some fields than others. It doesn't matter if you want a diagram, you could look at whichever diagram you feel most comfortable with or stick with that. Bottom line is the equations that matter. Okay? Okay. So today I'm going to build on this simplified long short-term memory, recurrent neural networks. And this is some work or some paper that appeared last year. And it just walks through ideas for simplification of the model without losing much performance. Okay? So we know that gated recurrent neural networks are becoming very popular because they demonstrated success in sample applications, in speech translation, and also in video sequencing. Okay? The gating mechanism apparently is very important for this stability, which avoids the so-called gradient explosion. You've been given that name, and that's what it is. And we're interested in producing these blocks for fast execution, potentially portable applications in training and processing. Typically, in neural network, we talk about training, and we talk about processing, which also has the code word or the inference. So you can say inference stage or training stage. And typically, most of the time, consumption is really in the training stage. That's why training stages are on the cloud. They take a long time. And then inference is obviously much faster, and people have been using various hardware in the training. For fast training right now, people use GPUs or even FPGAs as hardware platforms. These are the popular form now. Inference, there's some people who have dedicated hardware. They don't need to the GPU. For example, there's something called I guess it's TPU, which is Tensor Processing Unit, which is a new name that Google has came up with to describe their inference engine, which is a dedicated hardware that's tailored for recurrent neural network deep learning mechanisms, and it speeds up the process for inference application only. For training, still to this day, we're latched or with either the cloud or GPUs. You need a GPU for the training, but apparently you don't need it for the inference. Now, the inference concept is that after you train and you're happy with the parameters, you fix the parameters, and then you have the model, you just load those parameters in that model, and then here you go, apply your data and you do inference. Okay, without any training. So an example is this TPU is a Google dedicated ASIC hardware that can perform inference, and they deployed it on their systems and their cloud. So let me go back to this one. And we talked about LSTM. The architectures are composed of base memory cell, if I'm looking at it, and then replica copies of the same simple RNN to generate the gating signal. The memory cell is a weighted sum of a term from the S RNN, which is a simple RNN, and the previous memory value. Gating signals, they only need the state. This is the observation that we were motivating last time. For the gating signal, do you need all these other three terms? And essentially need, if you can capture the state in a good way, that perhaps the state will be sufficient to provide the gating signal. And if you do that, then you save parameters. So we can look at the memory cell or its activation as representing the state for the network. You choose either one is fine because they're equivalent. They have a transformation between them. And typically this transformation, nonlinear transformation, is invertible, meaning that if you have the state, you can get the activation. If you have the activation, you multiply, pass it through the inverse of the nonlinearity, you get this, the so-called memory cell or the state. So my point to you is that there are a lot of ways you can do in reducing this recurrent neural networks. Okay? So there's a host family of them, and I think we talked about the so-called LSTM1, LSTM2, the LSTM3, and this line here is reduction, so it begins here with the simple RNN model that I'm familiar with, goes all the way, the other extreme, the LSTM. And when you drop the input signals, you go down to LSTM1. This one, you're dropping the bias and the input signal. And this line is reducing the parameters line, just the visualization, LSTM3. So we discussed those three here. And I'm saying we can also have further reduction by going to LSTM4, LSTM5.
The performance here is relatively the same.
Well, I mean, it's
comparable in some.
So I mean, the case studies are there, and you could see which ones are doing well. Yeah. So obviously, it's not identical,
Right.
And but for the finite data sets that we have, you could say for the applications, the IMDB application, for example, the performance is the same. So we're going to see some performance metrics here. And that's what counts. But I'm just sharing the host of these families. And there are things further that one could do in terms of research. Now, if you can have this simple thing, or the so-called basic, the basic just moves from here by adding this one term. If you are at this point and you have a performance that is not blowing up, okay, then obviously you reduce the parameters tremendously and you're looking towards embedded, perhaps mobile applications. We looked at these things here, and we're gonna go and look at two more of those. So let's just review in terms of this diagram that goes from one extreme to the other, going down in terms of reduction of parameters. So the LSTM1, all it does is just take away the input from the gating signals. Obviously, you need the input for the network, but this is the cell of it. This is the body of the network. These are only the gates. So you count the weights here, and whatever the weights are, you have three of those weights and associated learning rate. So that's the simple modification. LSTM2, you just take the weight and the bias, the input and the bias, and associated weights. Very simple. 3 is you just have the bias, which is a vector now. Now you reduce two matrices 3 times. What is 4? So 4 is, I mean, just the numbering is that if you look at the LSTM2, you have it in this form. So your 4, we just kept this one even to be with this, but here you have a matrix times a vector. And 4 says, I have, let's say, n squared, this matrix. The gating just needs information about these guys. Now, if I convert this one into a pointwise multiplication with another vector, which means I reduce these matrices to vectors. So I have every gate output will be associated with one state, right? There's no mixing among the states. However, the mixing happening in this process, and then so here you have a full matrix that mixes the activation, which is the states, and this HT is going to produce this H, so the mixing happens here. What is the point? The point is I don't need a full matrix here to mix these states, because there's a mixing here. So even though I have a point-wise multiplication, I'm going to get gates each one from one component of the state. These states over time, they're mixed through the cell body. So the 4 thing says from 2 to 4, you're going to convert this matrix into a vector and do a point-wise multiplication. And similarly for the 5, you're going to look at number 1 and you convert any matrix multiplication into a vector multiplication by point-wise multiplication. So very simple. So when you see this dot with a circle, we converted that matrix into a vector, column vector, same size as the activation, and you go pointwise. No mixing here. You don't have a matrix to mix these states. And you get away with that because I'm already having mixing in the body of the cell. So all these states over time will be mixed. I don't need to mix them again here. So I'm reducing the parameters from n squared to n on average. And I have those gates. So that's 4. And then 5. 5 is similar to 4. Obviously, you just have the bias. So in these examples, we can go back to the MNIST data set and mimic the non-practical application, because we're creating from the MNIST sequences. We're not interested in showing performance. We just want to have a benchmark to compare various algorithms. And we're using the MNIST data because other people used it, so we can compare the performance here with other performances. So what do? There is the row-wise sequence, the MNIST, where 28 by 28, you take one row at a time, you create a sequence, 28 elements, each one of dimension 28. Okay, this has been accepted in the literature, and people have used that as a test bed for just looking comparative performance among things. Clearly, the performance here is not going to beat the convolutional network in terms of the application, but we're creating a sequence from a data that everybody had access to and people have used it over time. So here's a list of all the information. We run things for 100 epochs. We select hidden units, dimensions of 100, similar to what people have done. The type of nonlinearities, we can actually run things through the popular nonlinearity, hyperbolic tangent, sigmoid, and rectified linear units. These are the dominant kind of form of nonlinearity. This nonlinearity, applying it to the cell body. The sigmoid function is already the nonlinearity for the gates. If you talk about gates, you got to use the sigmoid because then it limits it between 0 and 1. The output dimension, we're trying to look at 10 classes, so the output is 10. The batch size is that, the batch size is that how many of these images we're going to run before we update the weights. In this case, every instance or every sample is really a sequence because the image converted to a sequence, so that's one sample. So we need 32 of these samples, and then we update the weights for the training. So this is the batch size, very important in the training, and you're going to see those in the libraries. And optimizers, in this case, in this experiment, is chosen to be the RMS prop. We talked about the RMS prop before. It's the basic gradient descent technique where you look at equivalently the variance of the gradients themselves over time, and you divide by the gradient. So I discussed that expression explicitly last time. So instead of having, so eta, you have an eta, and you add this other term, which is dividing by the really by the covariance or the standard deviation, we could take the square root of that, which really the strength of the gradient vector, which really implies that if the gradient vector is too large, you update slowly. That's what it says. If it's too small, you normalize the update. That's what it does. And the loss function is the categorical cross entropy, which we should all know by heart right now. Okay, we have the expression for it, and the categorical cross entropy mimics the Kullback-Leibel measure in one sentence, and also in the other way, technically speaking, it also helps by remove the derivative of the nonlinearity from the update law expression. So the LSTM number parameters, you can look at the number of parameters, you can count them here and multiply them, and you get the total number of parameters in this case for this experiment based on the choices of the hidden units and the dimension of the input, which is 28 in this case. And you look at how much time it takes among these different variants. There's the LSTM, which total number of parameters. We list the number of parameters in this, and obviously we use one platform using Keras. And for the platform we have, we compare, this is a CPU platform, we compare how much time it takes, seconds it takes for every epoch. So we're running 100 epochs. So you can do the math. The LSTM obviously is just a minor reduction, and then you go all the way. You see that number 3, the LSTM 3 here, is still the fastest in this case. And the reason it has only one parameter, which is the bias. These guys here, 4 and 5, they're similar to 1 and 2. But there's reductions in all these things. This is just sharing some performance data, and the performance data we have training data with a training accuracy, testing accuracy. So you can see, you can plot for all these different variants the performance. You could see the performance. So clearly, LSTM 4 in this case, I believe, I can't see it very well, but the colors. But they have, in this particular testing, based on this ADA, based on this particular performance, you see the performance that eventually after 100 epochs, they're all the same. If you stop at 20 epochs, obviously you see differences in performance. And you have, they all have above 98% in this case, and we see which ones are better in this ordering. Certainly, we still have the LSTM slightly in numerical values. You can see the numerical values. This case, you can have the type of nonlinearity activation is used for this experiment, and you have a grid of ADAs that shows you the performance of each. And really, typically, you wanted, using for the activation, which is the traditional way of using activation for this nonlinearity, you see LSTM is the fastest model, but obviously it loses in terms of accuracy performance. And we highlight here in bold for these experiments, the performance of each one of these cases. You have also experimental sigmoids, and you can see the difference when you have a sigmoid for the cell body. So this is just documentation, shows you all these pretty pictures of what the end result is, and have graphs in terms of the plotting for various eta, and it counts the number of epochs. So we adopted 100 epochs because in the literature we saw others in their experiments, they use 100 epoch to be able to achieve the satisfactory performance. Satisfactory performance would be viewed obviously when all the curves, the testing or what have you, level off. So for instance, for this case here, they all level off after 40 epochs in a way. So you don't see much performance, but in this case here, you see that this, for this eta, which is small eta, you have them at different rates, and some of them are still not leveling off. So this one speed up the process, because this 10 to the minus 4, this is 10 to the minus 3 for the eta. So that as you increase eta, obviously you have a speed up in the update. This is best results obtained by using sigmoid on this data set, and we look at the performance for this data. This is obviously initial experiment. It applies to data that's not really a practical application. It's a contrived application using the MNIST for the purpose of benchmarking and comparing various performing algorithms. So there's nothing much here. So in some etas, we discovered a lot of different things, but some of those things, when you use rectified linear units, we found, for example, the LSTM actually fails, which is reported before that it doesn't work and it does fail. But some of these other ones actually do not fail. So in this experiment here, for this particular parameter, eta, which is relatively large, some of these things start failing and some don't. And of course, for a smaller eta, none of them fail. So we're just exploring the limit of the parameter range of those things. That's not in any way just tells you that the limit of some maybe will be earlier than others, depending on the experiment. For the rectified linear, we have the performance. And in this case, one of them, which is the simplest one, actually the fastest one, performed well versus the LSTM. So that was an interesting result for the simplest, which we seek to make it better. So what this one says is that we were able to find a range, okay, that enabled this LSTM3, okay, to perform its best, yet the others maybe could not achieve it. Now, keep in mind, each one of these models, they have different number of parameters, which means each one of those models is going to have its own sweet set of etas. And typically, when you look at a library that's maybe Keras, when it gives us a tutorial, it gives us a tutorial for some, let's say LSTM, it gives us the etas that are good for that particular application. So typically you start with that, and then if you have a different model, you have to find your sweet range of a particular model because you're not having the same number of parameters. Keep in mind, when we derive the gradient descent, we have an eta, and that eta depends on the difficulty or the richness of the model that you have. So if the model is shrunk, you need to have a different eta for it, different update. So that's always the case. There's always a sweet range for parameters, and the libraries will have the sweet range for what they have because people have done experiments, and this is the set that they introduce for us. So if you ever have a dramatic change in a model, you have to find the sweet range of that model as well. And it's always good to have a range. And that range typically with the model, even though it's highly nonlinear, you need to know what the trend is. If you increase or decrease, are you improving or decreasing? That gives you a direction where you can improve or sweeten that thing. So in this summary of things, and I'm going to ask you to read the associated paper for more details, okay? It's very simple variation, but you can have a benefit by reducing computation. Even if you want to use the cloud, you're still going to have save time on this per epoch. And secondly, our goal here is to go towards mobile applications eventually. So you want things that may be not connected to the cloud for some cases that could be useful. And that also is important for security, because every time you go out from your local platform, you have added risks, particularly for valuable information. So the models having reduced parameters, variants are comparable in performance for this particular initial experiments, by no means complete, but we've had people who have done work on other models as well, particularly 2 sets of models that are available through Keras. And so that's, self-evident in terms of looking at the speed and the computational cost that we're talking about. Any questions? So another thing that's very important, which is in our textbook, which is shown in this graph. This topic, by the way, just to be, we're still in chapter 10 here looking at things. And sorry, I'm looking at the so-called bi-directional. Here it is. So 10.3 section talks about bi-directional RNN. The reason I want to discuss it, because we'll talk on an example in Keras which uses bi-directional. So what is this bi-directional RNN? Let's describe it through this picture. Conceptually, you have a sequence, and you're moving and applying the sequence forward in time. So you have a sequence, speech, let's say, and you move forward in time. And you create a corresponding recurrent neural network that moves in the same direction of time. And the idea, could we also have a sequence that takes it backward in time? So you have the same sequence, but you're going to run it through a network backward in time. So, and then you can maybe combine these two impacts together. So you have this H takes the input sequence, which is from this forward in time, takes the input, and then this HT minus 1 is going to feed the next HT, the next HT plus 1, and so on. So the dependency among the elements are forward in time. The idea was, if I have a speech, I want to also learn about the dependency backward in time. Why is that in speech in particular? Sometimes when you say a sentence, the last word of the sentence could depend on the first word, and also you could have the first word depend on the last word. So there's dependency both ways. So they're trying to capture that information in representing the sequence. Because you have a sequence, you want to capture any dependency forward and any dependency backward, right? So, and this is really helpful also in translation applications, where you have a sentence and sometimes the last word really gives you more meaning to the sentence, or the first word, and so on and so forth. So here's the diagram, which is a cartoon that just captures information. So the sequences here, these guys here represent the activation for one recurrent neural network, whichever one you choose, okay? And you have another neural network which is represented by this activation G, where it takes the last value, but it moves, as you can see it here, this guy is going to depend on this guy and this guy, right? So this is actually, you can say, take the same recurrent neural network, but you're going to apply the last element to it to generate this previous element, and then so on. So you have it backward, okay? And then the output from this guy and the output from this guy. So this is the first element here, and this is this element. Both of them going to generate or contribute to the output. So the output will be a weighted sum, if you wish, of contribution from two instances. One, this instance is a recurrent happening backward. This is forward. What is the connection? Whenever we have a recurrent neural, we need to initiate it. When you have a dynamic system or recurrent neural, you need to have the initial state to move forward, right? So you have the instant at time t and some initial state, and you move it sequentially. So in this case, this network, it starts at the end. So you look at the last element of the sequence, you supply it, and of course you need some state at this point here. But then you generate this one backwards. So the next thing, you take this sequence and so on. So the bi-directional is that we process a sequence by two networks, one forward in time and the other one backward in time. And then we get the two results of these networks and we weight sum them to get the output. That's the total mapping. And this is bi-directional, and you can see the sense of it, particularly in languages and language translation, language understanding, bi-directional. Okay, so that's another concept. It just builds on the same LSTM, just you sandwich them and how you're going to do it. And in this case, you have bi-directional. And the other concept that you're going to come across is that, can I also have multiple of these blocks? Recurrent neural network, one feed into another one. Do I, in this case here, we both went to the output. But you can say these two guys may go to another layer of recurrent neural network. In other words, the outputs of these guys will be sequences that feeds into another. So you have layering of recurrent neural network. Often, in practice, people stop at 3 or 4 layering, okay, of these networks. And the idea is the sequence is your raw data that comes in. It's a sentence. And this layering is going to give it multiple representations, stage representation. So it's like you have the first representation of the data, the next representation of the data, until you fine tune it and capture essential features of the data. Similar to what we've seen in convolutional neural networks, when we start with an image, and then we have representations every layer that has fine-tuned expressions until we reduce it to something, hopefully, that captures essential information about the whole image. So you can deploy recurrent neural network in the same fashion by looking at layering. However, in most practice, people typically they adopt, the order of 4 layering of these things. Any questions?
Oh.
Yes.
So if it's bi-directional,
Yep. Sorry. Go ahead. Yep.
One a practical application could be like translating a sentence into a different language, and then the H is just looking at it from like first word to last word, you input the whole sentence.
Precisely.
And then G is just the opposite of the last word. Okay.
Precisely.
Okay, just
Precisely.
sure.
So it's like you have that, exactly. So the sentence is a sequence, and typically we start from the beginning to end to the sentence. So this one is also used, it's like you're flipping the whole sentence.
Mm-hmm.
Apply it to another sequence. and then you take those two for each corresponding instant, and you integrate them into an output, meaning that you weight sum them to an output. Very good. So that's the idea. So the idea is trying to capture dependency and in forward and backward dependency of a sentence. And they found this one to be very helpful, particularly, I think, my understanding in language translation or language, speech recognition as well. It's like if you have somebody talking to you, sometimes, you don't understand the sentence until you get the last word to get really the full meaning of what you have to wait for the whole sentence. And sometimes the last word changes your understanding of the sentence. So that's the whole idea. So it has both of these processing of the sequence and have them all integrated at the output. Any other questions? So after all this stuff, we'll go to Keras, examples. If I'm not, I guess I'm not connected here, huh? Should be. Need to. Excellent. Yep. Okay. So the section, if you look at all these examples, and I think that nicely they organized them here in terms of groupings, vision models, examples, and text and sequence models. So the ones that the bidirectional, here it is. You have IMDb bidirectional LSTM. So that's an example. Bidirectional. So if we walk through this example, so when you look at the definition of their model, so obviously they define the data. Now here's the model sequential. And they have an embedding. So this embedding layer is another important layer for speech or words. This embedding layer, remember what we did like in the, I guess, certain character, the character level model, RNN, the Python model of the character level generation of signals. There, we define the transformation of a character. We called it encoding. So you encode every character into its position in the list, and then that position becomes a position in a vector with all zeros except one in that location. That's how you encode it. Okay? But if you move to encoding based on word encoding, so we did a character, so in the English language, say whatever, 26, you add other character, maybe 32, 35. If you add the dots and everything else, that's finite set. So you end up with a vector like, let's say, less than 40. So if you go the character, that's why they went to the character level. But it's assumed that you say, no, I'm going to look at the text. I'm going to encode it based on the words. So if you have a huge text such as Shakespeare's whatever writings, look at the English language, you get lots of words. Whatever in the text, let's say, just pick some number, okay, like 1 million or something, okay, for example. Then are you going to do the same encoding technique, just creating a vector million dimension and just zeros everywhere except one? That's not efficient. So there are techniques where you actually create encoding. You have that vector, and then you create a mapping from that vector into a finite dimension. Right? So another level of encoding, you can say I'm going to have 8-bit kind of encoding, right? That's what we do like in computers, right? You have 8-bit, 16-bit, whatever encoding. You encode everything that you have in that. So they create an encoding mechanism to a finite dimensional vector, where every vector they want it to be have a good representation, different from other vectors. Okay, so typically they don't use the typical binary encoding that we have, because then the representation will be too close. Right? You have just 1 bit difference. Will be too close. So they create something where the representation is, I don't want to use the word orthogonal to one another, but at least far from each other. So every word will be kind of differentiated. Okay? So this embedding layer is, view it as a feed-forward neural network implementation, where you can have this inefficient, the position of a word, and it gives you a vector, let's say, of 64 dimensions. So here they selected to be the embedding layer, has maximum features. I think the maximum feature, and then 128. So the maximum features, let me see, helps you in reading this. So here they define the maximum features. So the maximum features, they're saying, this words, I have 20,000 words. Okay? Very interesting technique. The way they do it is that they have, if you have a collection of words like from a book, Shakespeare's textbook, you go around these words and you count the frequency of each word, and you rank them based on the frequency. This is just a technique that they adopted. So, and then based on the frequency, they order these words. So a word with frequency 5,000 will be in whatever position, okay? So something that's repeated a lot, it has high rank, would be like in the top, okay? And then in this case, they say, we're going to stop at 20,000 words. So out of, let's say, 1 million words, they're going to select the top 20,000 words. Okay? And then from these top 2,000 words, they're going to map them all into, in this case, this embedding, which is very important. Map them into, from the max feature is 20,000, you're going to map it to a vector of 128. So this embedding mapping, and I invite you to read up on it and Keras defines what it is. It just takes the population of the data that you have, which is the number of words in Shakespearean textbook. They say the maximum frequently used words are like 20,000 in this case. That's the maximum features. And then they want to map those into a finite dimensional vector, like 128 dimensional vector. Every one of those 20,000 words will have a representation of a dimension 128. So this just reduces the representation. When you go word level kind of representation. So that's the first layer. Any questions about the embedding layer? And I invite you strongly to go under keras.io and look at the definition of the embedding layer. So I'm explaining to you the technique that's been evolved or adopted is that you look at the frequency of a word, and if the word has high frequency, you care about it. If you have a word that only occurs once, that's unlikely, you don't care about it in terms of a translation. Okay? So in this case, they adopted the 20,000 most frequently used words in this textbook. And each one is going to have a distinct position in this 20,000. And then I create an embedding which transforms all these 20,000 words into a 128 dimensional vector representation. And you don't use just the traditional binary representation, which you could. Okay? they use just a mapping, a feed-forward neural network to train and give you a good representation of it. And this is called the embedding layer. So the embedding layer, view it as either already trained feed-forward neural network by other people. Okay? Google has its own embedding layer for the English language. They're trained very well. Or you could do a little training on it yourself. So that's the importance of the embedding layer. So all these big companies they're already trained some embedding layer for some languages. They say these mappings are the best representation for this language as far as we're told. And you can use it as is trained for inference to map words from a specific language into vectors. And these already been trained, and sometimes just use it as is without any training. However, Keras also allows you to monkey with these embedding layers and do some extra training as well if you want to. But typically it takes a long time to do that. And here it is. So after this one here, now the output of this guy is going to be 128, and it's going to be a sequence of length, max length. So what did they have, the sequence input? So max length in this particular example, if I missed it, it's 100. So you have 100 samples, sequence with a length of 100 in this case. So how does that relate to a text? So really what they do, if you give them a text, they take a sequence of length 100 to do the training. So they take a sequence of 100 words. They represent each one of those words with a vector of dimension 128. So I have a sequence of 128 dimensional vectors, right? And that's when you're going to supply to a recurrent neural network, and it's called bi-directional recurrent neural network using LSTM. And this LSTM is going to have dimension 64. So the input sequence has dimension 128. It's going to generate activation functions of 64. Okay? And it's bidirectional. And then you hit it with a dropout. In this case, somebody asked me last time about the selection of it. This is a heavy dropout, 0.5. 50%, they're going to be killed in this training to create stochastic nature. And then they have activation in this case. They have a dense layer. Activation is sigmoid in this example. Try using different optimizer and different optimizer configurations. And they have the compiling. They use the binary cross entropy. This is different from the categorical cross entropy definition. The binary, if you remember, we have it defined before, which is really the best in terms of eliminating the derivative of nonlinearity. And the metrics are accuracy, and you print your training, and here's the fit function. Use the sequence of input, the sequence of targets. The batch size is whatever batch size they use, which is the sequence samples, the batch size. Did I miss it here? I guess batch size is 32. So typically they, in practice, because they don't know any better for any application, they try a few numbers, and usually they try numbers with power of 2. Make it convenient for computation. And then number of epochs, 4 in this case, and validation data. You have another test data that's available. And this is the sentiment data, and I don't think they say much about how long it takes and what happens. Any questions about understanding this example? Yeah.
I'm a little confused on the bidirectional layer.
I'm sorry?
64. The way you're just after the embedding layer.
I'm sorry, I'm just trying to.
I
lost here my.
Mine's 36 and 37.
Okay. This one here?
Yep.
Yep.
So you're inputting a string of 128 words.
No. The dimension is 128. The string is 100.
Sorry.
the input length is maximum length. When we go upstairs, it's
so
100.
words. Sorry.
Yep, 100.
What's
100 words, and each word is represented by a vector of dimension 128.
Yes.
Yep.
What's the importance of the 64 in the bidirectional layer?
No importance.
Or
No importance. They just select their activation function via 64.
I don't understand what that's doing. Like, you're looking at 64 words at a time, or
No. This is the dimension of the nonlinearity, the output. The dimension, the output, so there's a sequence here of the same length of this sequence. So this is input of length 100. Each input signal of dimension 128 is going to generate a length of 100 of a sequence of H hidden units, each of dimension 64.
Okay.
Right? So each of dimension 64, just by choice. So that's, I guess, if we go back to the mathematical model, we look at the LSTM, right? So what does that mean? So this HT, each vector here is a dimension 64, each input XT of dimension 128.
Okay.
Right? So this 128 goes through this one and gives you 64. And then the next time gives you, so the sequence, 100 elements here and 100 elements here. But obviously, in the model, you're free to have the dimension here different from this one here. So they're saying, what is the dimension of this guy I want to choose? Because that tells you what LSTM size you have. So they're saying, I'm going to select 64. The input dimension is 128. This output is going to be 64. And of course, because they're bidirectional, we have another one, which is, we call it GT, which is also of 64. Why 64? Arbitrary. Just they figure that, okay, the data 128, and I just need something. And 64, maybe because we have 64 bits, could be, in the background of whoever did it. But they feel, obviously, if they tried 64 and didn't work, they will go to something higher. So apparently at 64, they got some good results. They, okay, this is a good example we can share with the community. But typically, in these numbers, because there's no other choice, you notice that the numbers they select typically 64, 100, 32. So 64 and 32 often related to the bit size of things, and the 100 just a number that you select. And if you try this one, the performance is not good, you say, well, this recurrent neural network is not rich enough, right? So I need something maybe higher. Every time you increase the hidden units, you increase the number of parameters, you get flexibility to the number. So you'd like things to be larger to have flexibility, but you don't want it to be too large because you're paying the price of having more parameters. So you'd like to be as low as possible, yet achieving performance. So I'm sure, like if you go through the mini project and you're given this one, you could change the dimensions and have another experiment. You see how, if no change, that means there was no need for the 64. You could have 32. Okay. So that's one example, and another example that is this pre-trained word embedding. So this example has the bidirectional, right? Has the bidirectional capability. It just uses LSTM bidirectional, right? This example, the pre-trained word embeddings, use convolutional. So you can read this one. It tells you this uses a different data set. It's called the 20 news group data set. Both of these new groups we used before in class last year. Okay? So because you have news groups, you have 20 news groups, and they're trying to classify, use it for training and testing. The idea is You want to read some paragraphs, and you want to say which one of these 20 groups this text belongs to. Okay? Eventually. So there's a glove embedding data can be found. So this glove embedding, people already trained some feed-forward neural network on these 20 news group to eventually have a compact representation of the words in this data set, which is the 20 news group. They have an embedding, and this embedding is called the glove embedding. You can download this from this source. Okay, so this glove DB is the data that's trained already, and it gives you the representation of these vectors. Now, let's see what the steps are. So you read all this stuff, which you can read, and then it says, so here's you go to the glove directory. So you download that file. You have this glove.db, which has the parameters of the network that they trained. And then you already have for us very useful techniques in accessing and reading the data. So here's a text file in this data. You read it. And here's the embedding. The embedding index word to coefficients. So every word that you have, it's going to give you its coefficients, representation. And so the lot of things here, the bottom line with all these steps is that you generate from all these steps, you're going to generate not there yet, sorry. So there's a data reshaping into a tensor, and here's the training data. So here's the embedding. So they create the embedding. I think there's a lot of details in the embedding matrix. So the reason they're talking about embedding matrix, now you have 20 classes, and you have train a 1D CovNet with global max pooling. So the sequence input. So they have the input, you have the shape, and the embedding sequence. That's what we want. So they have the sequence of input, and then the embedding layer generates embedded sequence. This whole stuff that you have here, reading the data, reading also the parameters, loading the parameters. It's all done, the footwork here. The bottom line, you're going to end up with a pre-trained network that maps words in this data set, 20 news group, into vector representation. Okay? And so you have the vector representation, which gives you embedded sequences. I want to see what the dimension that they've used here, and here's the embedding dimension. So which a parameter they define, embedding dimension 100. So maximum number of words, 20,000. Okay? Maximum sequence length. So the sequence length is how many words they take. Okay? So when they read something, they take the maximum would be 1,000. If it's more, they're going to cut that off, just stop at 1,000. If it's less, they're going to pad it with zeros. That's the tradition, okay? And all these details are described here, okay, in the example. And a lot of footwork here in preparing the data, which is already done for us, and it's valuable to read it. And the idea, you have 20 classes. You want to train on this existing 20 news group data set. And then you want to classify a new writing or new paragraphs of at maximum 1,000 words into which one of these 20 groups, okay? So that's more than the IMDb data set, which is just a sentiment that you read it and you say this is positive or negative, 2 classes. Now we have more challenging by looking at 20 different classes and trying to classify this one. So there are a lot of things that you can learn from here. And last year, I think we have in the mini project, which will be coming out, is exploiting those 2 examples. Initially, you're going to run these examples separately. Each one has its own data set. Each one has its own separate embedding. Okay? Embedding, just converting words of this data set into vectors. Each one of different dimension. 128, this one I believe is 100. So that's a pre-processing step that's done by pre-trained neural network, free-form neural, okay? You just read the weights, you put them in, you don't have to train this one anymore, okay? And then what you do, so this one just takes the word and gives you vectors, that's all, right? And then, of course, you want to train the network on the classification. So you train it on the data set, you take paragraphs from this data set, okay? You chunk it to at most 1,000 words. Each word is going to be represented by the corresponding vector based on the embedding. And you want to train it that this guy belongs to class 1 to 20, okay? And then after that, you want to test it on a separate data set. You say whether this paragraph belongs to this news group or that news group. So this is a very powerful application. And they've done most of the footwork in preparing things. And our job will be to focus on the neural network aspects. So in this case, what do they do? Once you have this representation, and I'm coming to the end of time here, just like they use conv one dimension, convolution one dimension. So this twists a little bit. If you remember when we talked convolutional network, we can look at 1 dimension or 2 dimension or even 3 dimension. Most of the focus on ConvNet is on 2D for images. But you can apply it also to 1D, and I think in the notes I began with the 1D. So you can do the same thing in 1D. So imagine your data is just 1D, and you're applying local kernels to this 1D, and you have it processed. So they apply it to 1D, and they say you have 128 features, and this is the size of the kernel 5. The activation is rectified linear, and you apply your sequence. And then you have max pooling 1D. The kernel is 5. And then you have another 1D, which applies to this previous 1D with the activation. And then you have max pooling again. And then 1D, activation, and then global max pooling. Global max pooling takes the whole thing. It doesn't just stop on one feature. And then you hit it with a dense layer. And then this dense layer is going to have the softmax. which interpret things of probability. So the output will be vector of the labels, which are 20 dimensional vector with a softmax, and it tells you this text belongs to which class out of the 20 with what probability. Okay? And sequence input and categorical and what have you. So we have already a well-defined and batch size, number of epochs, validation. I think it warns us at the beginning how much it takes. I think it says, or I hope it does. I thought it says something, but I don't see it here. So, okay, so I'm going to stop at this point. But those two examples, you're asked to study those examples in preparation of what will be coming through the mini project. So step one in the mini project, often it's simplest. Just reproduce the results, run it, get familiar with the example. So you have a head start now in doing that. And then we're going to combine those into something more meaningful. Use those two examples and having one example. Okay? Okay, we stop at this point.